Hi everyone, welcome back to another video. So we're still continuing on through the Practical Electronics for Inventors book, and funnily enough, I actually have an online lecture right now, but it's currently on low pass filters and high pass filters, etc. And I didn't. It's yeah, it's basically pointless sitting in it. So I decided, you know what? Instead of just sitting there for an hour not learning anything, I figured I'd just come jump back on this book and then get started with capacitors. So in the last video, we covered a little bit on mains power, which was a really cool graph. I enjoyed this. This was nice. I learned a fair bit, and then now I'm moving on capacitors. I'm really looking forward to learning about capacitors and inductors, at least to like a really basic level, because in every lecture of second year, they've been talking about capacitors and inductors, but not once was there any sort of basic explanation as to what they are. So yeah, there's a really nice YouTube channel actually, which I watched this video on. Let me find it. Um, Capacitors. See if it just comes up. Yeah, his one's brilliant. He gives like these amazing water analogies. Right. Let me watch an ad. Don't know. Hear it. Okay, skip the ad. So his water analogies here. Yeah, it's brilliant, man. Yeah, so I'd highly recommend watch his video. Um, his other one for inductors is really good as well. And the engineering mindset, 1.1 million subscribers. So obviously it's a good YouTube channel. All right, so let's crack on then. Capacitors. I mean, literally right now, I'm looking at my online lecture that's on now, and it's just these huge capacitor calculations about filters. Anyways, let's crack on. So capacitors. If you take two oppositely charged parallel conducting plates separated separated a small distance apart by an insulator. Okay. Yep. Such as got to press record on my iPad. Doing that. Now I press. Okay. So such as air, you have two plates and you have air between them, or dielectric such as ceramic, then that electrons can't flow through it. You have created what's called a capacitor. Now, if you apply a voltage across the plate of the capacitor using a battery, an interesting thing, electrons are pumped out negative battery terminal and collect on the lower plate, while electrons are drawn away from the upper plate into the positive battery terminal. The top plate becomes deficient in electrons while the lower plate becomes abundant in electrons. So you basically get a huge buildup of electrons here, right? This part becomes positively charged and this part becomes negatively charged. So I mean, technically, this the buildup of electrons is here. Okay, so this is saying that this is for the uncharged one. Yeah, because it's saying there's no voltage across it. So charging the capacitor, they're building up slowly, and then fully charged one, and then they've opened the switch so that it's not charging anymore. Okay, so electrons are pumped out the negative ion and collect on the lower plate. Yeah, that very quickly the top plate reaches a positive charge, and the negative plate reaches a negative charge. Accompanying the charge is a resultant electric field between the plates and a voltage equal to the battery voltage. So I'm kind of okay with this. I get this. So you got two plates. The top plate becomes Q plus, positively charged. This part becomes Q minus, negatively charged. Okay. Then what was the part about? So an electric field goes across it. Okay, so you get an electric field here. Electric field And then so then you get a voltage across them. And so this is going to be equal to supply voltage. The voltage equal to supply voltage. Okay, so the important thing to notice with our capacitor is that when we remove the voltage source, the charge, electric field, and the corresponding voltage remain. Okay, so let's do like this. We got a battery here, right? Positive. If battery, or let's just put source voltage. Oh yeah. If let's put voltage source. If voltage source is removed, this is why you don't touch a capacitor even after. I mean, they discharge fairly quickly, but you wouldn't touch a capacitor whilst it's either on or just you just turned it off. So if voltage source is removed, then charge. I didn't put charge in this bit here. Let's oh, I did here this charge. Let's charge. I like to use colors. There's your charge, positive and negative. So charge Charge, what else remains? Charge, electric field, electric field, and voltage. Voltage all remain. If voltage source is removed, charge, electric field, and voltage, they all remain. Cool. Okay. And the ideally this state of charge, it looks like my online lecture is finished now. Let's just close it. There you go. Cool. Okay. So ideally this state of charge will be maintained indefinitely. Huh? The state of charge will be maintained indefinitely. How's that? Even after attaching an earth ground connection to one of the plates, doesn't matter which one, will not discharge the system. Why is that? For example, attaching an earth ground to a negative terminal doesn't cause the electrons within that plate to escape to the earth ground where neutral charge is assumed. It might appear that the abundance of electrons would like to escape to the earth ground since it is at a lower potential. However, the electric field that exists within a capacitor acts like glue. Interesting. The positive charge in the upper plate holds onto the abundance of electrons on the negative plate. In other words, the positive plate. Oh yes, of course, because even if you ground one of the sides, you know, the electrons they want to meet up together. They want to get back together. So yes, I got it. Basically, if I can do a rubbish drawing, so you had positive charges here. I get it. You got negative charges here. Let's say there used to be a battery source here, but you disconnected it, right? Then now, if you then ground this bit here, these electrons here aren't going to flow down here. They're not going to do that because the charge is holding them together. So they're going to remain here. What will happen though is that if you then, put a lamp here and connect it to here, still these positive charged ones here aren't going to go into the lamp. But the moment then you connect this here, then they're going to go, oh, wait, we can meet. So then these rush this way, These wash this way, and then they power the lamp, which is cool because the capacitor has to do building up charge. Got it. Interesting. Didn't even consider that. Okay, so how can I put that into notes? I understand it at least. Okay, so let's put charge. So with voltage source removed, capacitor will remain charged indefinitely. Will remain charged indefinitely. Grounding one side would not work. Basically, just like with a 16-year-old teenager. So, the electric field holds the electric field acts like glue. The positive charge on the upper plate holds onto the abundance of electrons on the negative plate. In other words, the positive plate induces a negative charge in the grounding plate. So in real life, a capacitor so let's put ideally here because it's not real life. It's ideally a voltage source removed. Okay, so I like that. Not ideally. I'm gonna write down a bit about so the electric field. So I'm gonna test myself on all of this. I'm gonna turn this into questions and test myself. Electric field will act as glue. Act as glue. Positive charge on the upper plate holds onto the abundance of electrons on the negative plate. Positive charge on the upper plate holds on to, I don't know how to really put that in. The electric field will act as glue. The positive charge on the upper plate holds on to the abundance. Okay, just leave it at that. I can't really explain this bit in any other words other than that, and don't really understand that. That's okay. In reality, a real life charge capacitor that is charged and removed from the voltage source will eventually lose its charge. So in reality, where I live, capacitors eventually discharge. The reason for this has to do with the imperfect insulating nature of the gas or dielectric that is placed between the plates. So, because the insulator, okay, got it. So they're not going to go to ground or anything, but eventually there's going to be leakage between the two plates, basically, because the insulators used are not perfect. I just put, and there is some leakage. I mentioned book, and there is leakage. Oh yeah, cool. Yeah, this is referred to as leakage current. There's some leakage. Leakage called leakage current. So you have positive, negative. You do occasionally get get small amounts of leak. Okay. Depending on the construction of the capacitor, can discharge a capacitor within as little as a few seconds to several hours if the source voltage is removed. This can happen, or let's put more, and this can happen. Leakage current can happen in seconds or hours. What does it depend on? Depending on, okay, so depending on the quality of the capacitor, obviously, yeah. Depending on capacitor construction. Okay. To quickly discharge a capacitor, you can join the two plates together with a wire, which creates a conductive path for electrons from the negative path to flow to the positive path, thus neutralizing the system. This form of discharge occurs almost instantaneously. So, how to discharge? Connect both plates with short circuit, basically, right? With a wire. Happens instantly. Okay. The ratio of charge on one of the plates of a capacitor to the voltage that exists between the plates is called capacitance. Finally, I'm getting somewhere, people. I'm getting somewhere. Okay, so capacitance. Capacitance. I don't think I've ever heard a word as much as capacitance and not had any idea what it is. The ratio of charge on which one of the plates of a capacitor to the voltage that exists between the plates is called capacitance. So analysis. So C is equal to Q, which is, I assume, is like charge, divided by voltage. The ratio of charge is called capacitance. Capacitance related to charge and voltage. Cool. C is always taken to be positive and has units of farads, so you can't get negative capacitance. Okay. So C is always positive. Units farads. Farads like Harrods. That's F. 1 farad is equal to 1 coulomb per volt. I'm not really comfortable with coulombs, but okay. 1 coulomb is like millions of electrons flying past 1 point in 1 second, right? So, 1 farad, okay? 1 farad equal to 1 coulomb divided by 1 volt. So F is equal to C divided by V. But what's up with this? This C is not capacitance. This C is coulomb, so that's a bit confusing. I'm just gonna write coulomb. So capacitance is equal to charge divided by voltage, and a farad is equal to coulomb divided by voltage. That sounds like the same thing to me. Okay. Devices that are specifically designed to hold charge, electrical energy in the form of electric field. So charge is electrical energy in the form of electric field, are called capacitors. Devices that are specifically designed to hold charge. So devices designed the hold charge is equal to capacitor. Figure 2.93 shows various symbols used to represent capacitors, along with a real capacitor model. Where's the real capacitor model? Oh, there. Okay. This is the real capacitor model. I don't get that. What does that? Why is there an inductor there? There's a resistor, a capacitor here, a resistor, and another capacitor, and that's a real capacitor model. Okay, I get the ideal. Oh, leakage. Okay, yeah. So you just, for example, this is RL is going to be a very high resistor value, and these are the symbols for. Let's take a note of some of the symbols. I think we should all. I think we all know what capacitor looks like. I don't know what the curve means. So this is saying it's a fixed one. Okay, then you have polarized. Okay. Fixed. And then you've got polarized. Okay. Got a variable capacitor. Interesting. Variable capacitor. Alright. Don't really know how that works. What do the plates move inside? This is a confusing symbol. Arrow on this here. No. Variable. So there's a trimmer capacitor. Alright, I'm gonna skip that. I don't feel like I need to know, need to know that one. So let's. Alright, so I feel like this ideal versus leakage is probably an important point, especially if I'm going to be using multisim. Maybe I could start if I'm going to design capacitors, circuits with capacitors. Probably know that. So let's put real capacitor model. Okay, so deal. You got the real deal. This is a capacitor. Cross it. RL. Very accurate. Okay. All right. We'll read this bit and then we'll do the examples in the next video. Try and keep this video short. It takes me such a long time to read for one, and then two to learn stuff that I feel sorry for you guys. Okay. So I don't feel sorry for me because I'm actually learning stuff. So the equation C is equal to charge divided by voltage is a general one. It really doesn't tell you why one capacitor has a larger or smaller capacitance than the other. Okay. Why one has a larger or smaller capacitance. However, in practice, when you buy a capacitor, all you'll be interested in is the capacitance value labeled on the device. A voltage rating and other parameters are important too, but we'll talk about them later. Most commercial capacitors are limited to a range of 1 picofarads, is that trillions? By the SI units. SI units. Pico. Not even on here. So what's this? Milli is 1,000, micro is a million, nano is a billion, so pico must be a trillion. Pico, there you go. 10 to the 12, so a trillion, right? 6 zeros is a million, 9 is a billion, then you got trillion. Pico is a trillion. So most capacitors, we put values. Most capacitors are between 1 picofarad, which is 1 trillion. Then how do you put that? Like 1 trillion. 1 times 10, 12 farads. Up to 4,700 microfarads. Right? Micro is million, right? Micro. So up to 4,700. So they're all tiny. 4,700 UF microfarads. I suppose in your circuit, you don't want large builds up of voltage going on around the place, do you? So probably makes sense. Which is 1 times 10 to the 6. Write down. I was only to write down that it's 1 million. Like I remember that. With typical values for the first 2 digits of the capacitance of 10, huh? 10, huh? Okay. Okay. Do I need to know that? As long as I get that the range is tiny, do I need to know that they're 10, 12, 15, 18, 22, 27, 33, 39, 47, 56, 68, 82, and 100? No, I'm not going to write down. That's too many numbers. Okay. Having a wide range of capacitance allows you to store different amounts of charge for a given potential difference. Okay. Having a wide range of capacitances allows you to store different amounts of charge for a given potential difference, as well as maintaining different potential differences for a given charge. Read that again. Okay, having a wide range of capacitors, yes, allows you to store a different amount of charge. Okay, because I suppose you're not storing voltage, you're storing charge, right? Yes. For a given voltage. Okay. As well as maintaining different voltages for a given charge. As well as maintaining differences. Okay, I don't get that. With the appropriate capacitor, you can therefore control the storage and delivery of charge or control potential differences. Okay, I don't see how you're controlling voltage, because if you just have a voltage source, how are you controlling voltage? Yeah. All right. I don't feel like maybe I shouldn't round the video up on a confusing note, but yeah. Hopefully that made sense to you. I kind of get it, and I'm happy that I've had a little brief introduction to capacitors. I do feel a little bit better about it. I think the main thing that I need to take away from here is that the capacitors are storing charge, and that bear in mind that they're between a range of 1 picofarad and 4,700 microfarads. Okay, interesting. All right, so in the next video we'll do these example questions. Really look forward to these. I'm really enjoying this book as well. Actually, the fact that they introduce a topic to you and then they give you some nice questions about it with the answers right there. Some of the other books, this is crazy, right? You do the exercises and then the solutions will be on like page 9,900 or 1,000 or 1,200. So you do the question, you want to go look at the answer, you scroll all the way down, go look at the answer, find it, then come all the way back up. Headache. This is beautiful. Look, example 1, answer. Example 2, answer. Brilliant. So, all right, I'm looking forward to doing that